La 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 la. All right, so Dr. Smith here. Problem one on this little review set we got here for energy and stuff is the one where, oh, come on, draw. Yeah, that's okay. It's the one where Luke is, this is on the Battle of Hoth. Luke's snowspeeder's crashed, and he needs to use a cable to lift himself up to the belly of an AT-AT so he can toss a grenade inside heroically and destroy the thing. So there's the AT-AT with its horrible little legs. This is really just the bottom of the AT-AT. I want some weird mode where it's like I'm drawing with like an origami pen or something, or not an origami pen, but like a calligraphy pen. You know, it's just it's annoying. Anyway, so there's the underside of the AT-AT. Here's the ground. So we want to know the power that Luke's little winch belt or whatever it is has to produce to lift him 15 meters in 5 seconds. Okay, that's part A. So what I'm going to say is we're going to start stage 1, or state 1 is going to be Luke on the ground here. There he is. And then state 2 is going to be when Luke is up right under the AT-AT. Okay, so, and he goes up 15 meters. So first thing we got to do is we're going to deal with gravitational potential energy here, which means we've got to define some level where potential energy from gravity is 0. So I'm going to arbitrarily say the surface of the snow is where that is 0. So for state 1, we're going to say he starts from rest. And I probably didn't make this quite clear in the problem, but what I really intended was simply that Luke sort of straps the cable on, and then it lifts him at a constant speed, and then when he gets to the top, he just stops. And the speed he goes at is, not terribly high. It's about 3 meters per second on average. And really, the whole point I was trying to get here was just that the power required is basically what he is basically just what the work is what the winch needs to do to overcome gravity. Okay, so to start, he's got 0 potential energy. He's got some small speed as he goes up. It's Luke's mass times 1/2 times v squared, but it really doesn't amount to much. So we can just sort of neglect that for the first part of the problem. And then at state 2, when he's at the top, he's got k equals 1/2 m v squared, but that's basically neglect. We can treat that as negligible. And the important thing is that his potential energy changes. So mgh. So now he's risen to height h, 15 meters, g, Luke's mass. This is all fine. So the work done between 1 and 2. I mean, look, obviously his mechanical energy has changed, right? His mechanical energy is the sum of kinetic plus potential. Okay, so if we look at these two, and I'll do mechanical energy in a different color, like, purple. So mechanical energy is effectively 0 here. If we're treating this as a small amount, and this is the same small amount. Mechanical energy is 0 at stage 1 when he's at the bottom, and mechanical energy when he's under the walker is then just his potential energy there, which is mgh. So the work done between state 1 and state 2 is going to be the mechanical energy at state 2 minus the mechanical energy at stage 1. So you can see that the mechanical energy is not conserved because some work is done, and the amount of work that's done is the change in the mechanical energy. So the work done between 1 and 2 is mgh. So it's just the work necessary to lift Luke to the bottom of the walker, and the power required is the work done divided by the amount of time that passes. And so that's, if you really want to flesh it all out, mgh over delta t. So one way to look at this is, this equals, I guess it's going to be Luke's mass of 75 kilograms. I'm using 10 for g, so I'm going to use 75 kilograms times 10 for g, 10 meters per second squared. It's close enough, right? Times, sorry, not 12 meters, 15 meters, okay? All over 5 seconds. And what this comes out to, for me, is 2250 watts. If you use 9.8 for G, you'll get slightly less. I'm not sure how much, and, well, frankly, I don't care. So that's up to you. the other way to look at it is that he's going up at this constant speed, okay? So he's basically going up at a constant speed, and the speed he's going up at is the height he has to ascend divided by the time it takes. And that is going to be, in this case, 15 meters divided by 5 seconds, which is 3 meters per second. And over that whole time, if he's going at constant speed, the winch needs to exert enough force to counter gravity on him. So you can think while he's ascending at his constant speed, if we did a little free body diagram, you'd have this force that the winch is applying, and you'd have mg going down, and these two would have to be equal in order to have a constant speed and have no acceleration, right? So you could say that the force the winch has to exert is more or less a constant and equal to Luke's weight, and the power, so you may recall that power, this is kind of useful, is F dot V, right, for the force exerted on an object moving. So in this case, since F is acting upwards and V is traveling upwards, we can just multiply the force times Luke's speed, and then we get, mg times, and so the force is mg, right, and V is h over delta t, and you can see then this gives us the same answer, mg h over delta t, as we got over here. So both methods give the same answer, and they're both equally valid. No problem. Either way you want to do it is fine. Okay, so that settles us for part A. So that's the answer to part A, is 2250 watts. Now let me look back at the let's see, this is the page, and oh right, okay, so then after releasing himself from the underside of the walker, he he tosses the grenade in, and then he lets go, or he lets the let's see, where's my thing? There we go. Lets the cable release, and so he falls to the ground. So when he hits the snow, I'm going to call that, there we go. I'm going to call that state 3. So then he falls, and at state 3, there's Luke hitting the ground. You can see the wind knocked out of him in my artistic portrayal. So I'm going to take a little bit of a liberty and just sort of kill this part because I need some space. Thank you. And so at state 3, his kinetic energy is 1/2 mv squared, and his potential energy, he's back to the ground now, so his potential energy from gravity is 0. And so if we look at state 3, our EMAC for state 3 is 1/2 mv squared, where V is that speed that he hits the ground at, right? So now a fall like this, if we're ignoring air resistance, and we usually do, you can treat it as a case where mechanical energy is conserved. So going between 2 and 3, there are no non-conservative forces acting. So we can say that the mechanical energy at 2 equals the mechanical energy at state 3. Okay, so his mechanical energy up here, potential plus kinetic, equals his mechanical energy down here, potential plus kinetic. All right, so pardon me again while I, let's see, well, I don't want to erase that, but pardon me again while I erase a few things, and there we go, thank you. Okay, so now we can take this fact that these two EMACs are the same, and we can do, ooh, my phone just buzzed, that probably means my wife is on her way home. Hooray! So EMAC at state 2 is mgh, and at state 3 it's 1/2 mv squared. And so you can cancel some things, and what you'll get is that his speed when he hits the ground is, so the square of his speed when he hits the ground is 2gh. Okay, that's just algebra on this. You multiply the 2 over, you divide the m out. And so obviously then his speed is square root of 2gh. You've probably seen that result before. And again, if you use g for, or if you use 10 for g, like real scientists do, real awesome scientists, then you will get v equals the square root of, so it'd be 2 times g is 10, and then h is 15. So it's 2 times 10, which is 20, times 15 is the square root of 300, which ends up being, if you really want to be sort of super math nerdy about it, 10 squared root of 3. And so his velocity when he hits the ground, or his speed when he hits the ground, is about 17.3 meters per second. So that's the answer to part B. And finally, we have part C, which is where he has sort of fallen and sunk into the snow a bit. And he sinks into the snow 0.3 meters, I think I said. So let's take him down a distance like that. So this distance I'm going to call D. And now Luke has sort of made a pit in the snow. And this is horribly, disproportionate, because it's actually, he doesn't fall in, this far relative to the size of his body. But this is a little stick figure, whatever, Luke. Okay, so D is how far down he falls, and D is 0.3 meters. So he sinks that far into the snow. And so once again, I'm going to have to beg your... Oh, wow, that's ugly. Let's see. I'm going to have to beg your forgiveness and do a little cut and paste. Not that. So I'm just going to grab this puppy, and that's our answer for part B. And wow, that totally didn't work. So let me see now if I can grab this thing, and then... Ooh, okay. This is what's so funny about these videos, is you can watch me discover features of these paint programs I use. Okay, so that's the answer to part A. Here's part B. Come on, stupid mouse. There we go. Okay, so there we go, part B. And then for part C, oh crap, now I gotta erase stuff. Oh, fascinating stuff, I know. Let's see. Erase all that crap. Dang it. Alright. Doink, 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 doink. Okay, so let's just we'll stay there. And I'm gonna call this now where he hits the ground, or where he's sunk into the snow. I'm gonna call that state 4. So that's where he's down in the snow. So, state 4, his kinetic energy is now 0. His potential energy is now negative mgd, because he's sunk D into the snow. He has a negative potential energy because we said at the beginning, well, I said, that the potential energy from gravity when he was on the surface of the snow was 0. So, if he goes up from there, he gets a positive potential energy. If he goes down, he gets a negative potential energy. Important point about potential energy is that it's all relative. All that matters is that you get the changes right. You can pick any point you want to be 0 potential energy, and then do everything correctly relative from there, and you'll get the problem right. So now he is sunk in the snow. Here he is. And so if we look at the change of potential energy between 3 and 4, so E mech 4 minus E mech at state 3. So for state 4, E mech is just this negative mgd, because he has no kinetic energy. He's stopped. So, boy, I'm sorry this pen is so ugly. I mean, not that my handwriting is so great, right? But still, this is just ugly. So we want to find the change in mechanical energy between state 3 and state 4. And one thing you notice here is that now the mechanical energy at state 4 is negative mgd. Okay, the mechanical energy at state 3 is this 1/2 mv squared, where v is our answer from last time. But something tricky here, or sneaky here, a clever way to do this, is to notice that EMAC 3 here is actually the same as EMAC 2, right? Because remember, these are the mechanical energies from when he started here and fell down. Mechanical energy stayed the same all through this. So we can substitute in this expression here for EMAC 3 down here, see? But what is sneakier, and ultimately works better, is to take our EMAC 2 here, because see, these two are actually the same. Remember, that was how we solved part B, and substitute that in down here. So what you get there is negative mgd minus this expression, mgh equals, and so I didn't say what this equals, but the change in mechanical energy between 3 and 4 is the work done by non-conservative forces. And in this case, it's the work done by the snow as Luke compacts it. Snow, I'm going to call that W subscript snow, okay, which is, I know, is super hard to decipher. This is the word done by the snow. Sorry, the word done by the snow. The work done by the snow is negative mgd minus mgh. So work done by the snow is really negative mg times d plus h. And the reason why this is a negative number is because Luke has kinetic energy when he hits the floor here, or he hits the top of the snow here, and he loses kinetic energy, and he doesn't, he gains a little bit potential energy from gravity. Wait a minute, sorry. He gains a little bit from losing gravity potential energy. Okay, I'm fumbling this already. But here's the point. Mechanical energy at state 3, when he first hits the snow, is clearly positive, and it's going to be a decent number, okay? When he is done sinking into the snow, it's a negative number. That's a negative sign there, right by the MGD. Trust me. There, negative. That looks a little better. Negative MGD. So clearly he loses some mechanical energy between 3 and 4, and that's what goes into the snow. So this work here is negative because he loses mechanical energy. The system loses mechanical energy. And if you calculate all this out, the work done by the snow, you can find it. But I'm just going to finish this off symbolically and say what we really were asked for in the question was the force exerted by the snow. Well, the force the snow exerts on Luke, or the average force the snow exerts as he's going up, times the distance he sinks into the snow, is going to equal the work done by the snow, right? Because this is just F dot delta R, but since the force of the snow is pushing up, and the distance he moves is going down, those are in parallel directions or anti-parallel, depending on your point of view. And so you can pretty easily solve this. So you can say F exerted by the snow equals the work done by the snow over D. And the work done by the snow we found up here. So this is negative mg times d plus h all over d. So if you really want to sort of pretty it up, you can. I guess you can do a little bit of math. But the force exerted by the snow, and really we just care about the magnitude, so don't worry about the negative sign, is just going to be mg times 1 plus h over d. Okay? And what it comes out to, basically, I mean, you don't have to simplify it this much. You can plug in here, whatever you want. What it comes out to is, let's see, if I recall correctly, well, I can't recall correctly. So it's a mass of 75 kilograms times g, which is 10, so 750, and then height is 15 meters, d is 0.3 meters, so 15 over 0.3 is 50, plus 1 is 51. So it's 750 times 51. Oh, I don't know. What the hell is that? Let's see. 750 times 51, 3750. 3750. Sorry, 37,500. I believe it comes out to be around 38.3 kilonewtons. And that is your answer for part C. So, quite a bit of force the snow exerts on him, but hardly a surprise because, hey, he's, smashing into it pretty fast and stopping at a pretty slow. In reality, the snow probably couldn't exert this much force, so Luke really would make a nice little cave in the snow. But that's not what they showed in the movie. They showed him just like flopping out on the top of the snow, and then he could watch the walker explode. All right, fascinating stuff. On to problem 2 next.